Good morning. This is Dr. Kumar Arya, Associate Professor in Department of Chemical Engineering at IIT Jalandhar. So, in continuation to our previous lecture, today I am going to explain the power law fluid flow in a slightly tapered tube. Previously, we have solved this problem in case of cylindrical tube of uniform cross sections. Now, here we have considered a slightly tapered. So problem statement, a fluid of constant density rho is in incompressible laminar flow through a tube of length L. The radius of the tube of cross circular cross section changes linearly from R0 at the tube entrance at Z equal to 0 to a slightly smaller RL at the tube end at Z equal to L. Here we have to determine the flow rate versus pressure drop relationship for the fluid that can be described by power law models, or you can say a polymeric fluids. So in this case, the tube is like this. So you have a tapered tube. So here you have a bigger diameter, and as you will move along the axis of the tube, the cross section is continuously decreasing and it is ending up a value RL at the exit. So for this, the applied pressures, the pressure at Z equal to 0 is P0, as Z equal to L, the pressure is PL, and flow is being considered in axial directions, so there is no flow in radial direction. So previously we have derived the expression for volumetric flow rate for power law fluid flow. So this derivation was being done in previous lecture for power law fluid flow in circular tube or having uniform cross section. Now this cross section, because in case of this also, if you say that we have the flow here, so if you time being the power law fluid flow, so the expression would be valid here. So whatever mass would be entered inside the tube at this, same mass will continue throughout. So that volumetric expression we will means convert it into the mass, so that the mass conservation equation would be applied uniformly throughout, because mass is conserved quantity that will not change by changing the cross section. So in this case, this volumetric flow rate is being multiplied by density rho to get the mass flow rate. So in case of mass flow rate, the expression would become here. So both the sides here and this side, you have introduced one term with density. So density here. Now we are rearranging these whole terms in terms of R and delta P. So we can say here, so this particular term is being taken W. So here we have transferred here R to this term and this side. So we have taken here exponent term only to this side, rest of the term to this side. Now we have again actually remove this exponent by multiplying by nth power actually. So in that case you will get power n here, so it will become 1 by r to the power 3n, and this exponent would become now 1 actually. So this is the expression here, so we can rewrite this expression for in terms of delta p. So only for delta p the expression would become this: minus 3n plus 1 multiplied by w divided by n by rho uh, to the power n, and here 2 mu naught divided by r to the power 3n plus 1. So but here the delta p is actually minus rho gz plus delta p upon del z, For horizontal case, gz equal to 0 and delta p equal to del p upon del z. So this is the expression for delta p. So we can substitute the expression of delta p from here in terms of z. So we will have delta p del p upon del z, but we given by this equation. So in this only we have just substituted the expression of delta p. Now we see here for tapered tube also the mass flow rate doesn't change, so therefore we have considered mass flow rate. So our equation approximation is valid for differential length z of tubes whose radius is slowly changing with axial distance r. So your del p upon del z term would be given by this particular expression here. So here you have r. So now r is getting changed with respect to z. So we have just put a suffix here as z. So we can say the instantaneous value of r actually. So this pressure will decrease as z will increase. So as you will move to z to this exit side, your r will keep on decreasing and therefore pressure will keep on decreasing. So approximation we used here is flow between non-parallel plate surface is being treated locally at flow between parallel surfaces. This approximation is being called as lubrication approximation is because it is very oftenly used in lubrication theory. So lubrication approximation says that local applications of one-dimensional solutions and therefore may be referred as quasi-one-dimensional approach. Now we have here this RZ, so we want to find the expressions of RZ. So if we will see here, we draw the tube and this is the center line. So this is the center line here. So at the exit, the radius is R. At the entrance your radius is r0. So we can find here, if we find here this particular the bigger triangle here, this one. So this particular dimension is r0 minus rl, and the smaller triangle here, if we draw here at any position z, so we have corresponding radius is rz. So here this difference would be this one would be the difference r0 minus rz. So we are somehow correlating rz to r0, rl and z. So we can calculate tan alpha from this smaller triangle. So that is r0 minus rz divided by z. Then tan alpha in this bigger triangle. So that is this r0 minus rl divided by full length of the tube. So we can equate both the tan alphas here. So we can equate here, we can get the expression of rz equal to r0 minus rl divided by L multiplied by Z. So RZ equal to practically R. So you will get here RZ expression is R0 plus RL minus R0 divided by L multiplied by Z. So from here we will get the relation between dr over dz. So if we want to differentiate this, so if you differentiate dr over dz of this equations, so you will get RL minus R0 divided by L. So for your dz equal to L upon RL minus R0 multiplied by dr. So now you have the expression of dz. So this dz expression can be substituted back at this particular place here. So here if you will just substitute here in pressure equations, so you have access the pressure equation here, pressure gradient del P upon del Z equal to minus 3n plus 1 upon n sorry, into W upon pi rho multiply power to n 2 mu naught Rz to the power 3n plus 1. So here the substituting the value of dz from here, so we can substitute in this particular equation here. Then we can segregate the variables here. So this side we have left with p and rest of the term we have taken to this particular side, and we are integrating for entire radius because this is the function of r only. So this is R, so this is R0 to RL. So corresponding pressure is P0 to PL. So if we'll integrate that, so this would be on left hand side. So this term would be, so there is no change in this equation from here to here. Only thing, this term need to be integrated. So this is minus 3n minus 1 plus 1 power. Same thing, need to go to the denominator part and substitute the limit here, R0 to RL. So if you substitute the limit here, so you will get this particular equation here. Then you have to rearrange it. So if you rearrange, you will get these equations. And after that, you just arrange it further. So you will get taking R0 to one of the sides, because R0 is constant. So you will get R0 upon RL to the power 3n, and this minus 1. Here RL upon R0 equal to 1. Taking RL upon R0 as lambda, so we can write in terms of we can rewrite this equation again in terms of new variables which we have considered just now. So lambda, in terms of the lambda equation, becomes something like this. Now we can rearrange this again in terms of the lambda here, find the equation for delta P. So we are rearranging in segregating the powers and everything. So we will get this term delta P upon 2 mu naught L 1 by n 3n lambda minus 1 divided by lambda to the power minus 3n minus 1 to the power whole to the power 1 by n multiplied by R0 to the power 3 plus 1 by n minus 3n plus 1 divided by n w upon pi rho. Now we can write for only for mass flow rate terms, so we keep here mass flow rate, rest of the term to the right hand side. So right hand side is this term here, so we can again write it in final form here, again this one. So the same equation, only thing we have rearrange in terms of R naught multiplied by density, then delta P rho naught upon 2 mu naught by L to the power 1 by n. Then here you have 3n bracket lambda minus 1 bracket close lambda to the power minus 3n minus 1, the whole to the power 1 by n. Now this one we can write here, so this is the same equations as we have here. So this you can write now in terms of volumetric flow rate. So because this mass flow rate divided by density would become now the volumetric flow rate. So from here to here, just only thing you have divided this equation by density. Now if you see here, so this particular term inside the bracket is known as taper corrections, and this equation is valid for flow of the polymeric fluid flow in slightly tapered tube. Okay, so this is the expression. So here we have just taken the uh, pressure equation derived for polymeric fluid, and then we have considered is the lubrication approximation, integrated that for the mass flow rate, and finally we end up the expression for volumetric flow rate in slightly tapered tube. And here we got the lubrication, means a tapered correction shears. So this is all about the flow of power fluid flow in slightly tapered tube. Thank you. In case of doubt and suggestions, you can write as a comment. Thank you very much.